we want to calculate x to the power n or 7 to the power 5 or x to the power y. So since we cannot do this for large values of the power, so we will do this using smaller powers. But uh, I know you can do this very easily using loops, and the goal of this recursion lecture is to make you do whatever you can do with loops with recursions. So uh, now let's see some approaches to solving this problem with recursions. So here I have presented four recurrence relations. For example, notice that this is the smallest and easiest looking recurrence relation. So we want to calculate a to the power n. So somehow if we knew a to the power n minus 1, then we could just multiply an additional a, then we could get a to the power n. So this is actually you guys do this using for loops. So that this is the easiest looking equation, and this is the most used approach. You guys do this using for loop. In the n-1th iteration of the for loop, you calculate a to the power n-1. Then in the next iteration, you just multiply an a. So so if we use this approach, then let's find 7 to the power 11. Okay, so let's go to Corel. 7 to the power 11. So we want to calculate this value using that approach. So that recursive relationship is like this: a to the power n, and which is a to the power n minus 1 into a when n is greater than 0. If n equals to 0, then we just return 1. So we want to calculate 7 to the power 11, so which is, we have said that we want to if we knew somehow 7 to the power 10, we could just multiply 7, but we don't know 7 to the power 10. So we will call this recursion again. Then in that recursion, if we somehow knew 7 to the power 9, we could just multiply a 10. Then we don't know 7 to the power 9, so we call this recursive function again. Then in that recursive function, what we do is this is 10, or sorry, 7. So if we could knew 7 to the power 8, we could just multiply a 7 to get 7 to the power 9. So we are just decreasing the power of 11 to 10, then to 9, and then to 8. So at each step we are decreasing the power of n by 1. So this will take almost 11 to 12 iteration to get to the 7 to the power 0. So when 7 to the power 0, since when the power is 0, we just return 1. So in that case we'll just return 1. So let's do this for a much smaller value, because I cannot write 11 iterations from top to bottom. So now let's say we want to find 7 to the power 5. So 7 to the power 5 is actually, if we somehow knew 7 to the power 4, then we could get 7 to the power 5 like this. Then if we knew somehow 7 to the power 3, we could get 7 to the power 4 like this. Then if we somehow knew 7 to the power 2, then we could get 7 to the power 3 from here. So if we knew 7 to the power 1, then we could multiply 7 and get 7 to the power 2. And if we knew 7 to the power 0, then we could multiply 7 with it, and we could get 7 to the power 1. So since 7 to the power 0 it goes to this if case, the base case, we return 1. So 7 to the power 0 is actually returned 1. So we multiply 1 with 7 and we get 7. So we return 7 to 7 to the power 1. So 7 to the power 1 is actually 7. So we multiply 7 to the power this 7 with this 7, then we get 49. So we return 49 here. So 49 into 7, So 49 into 7, which is um, 49 and 7 returns 343 here. So we have found that 7 to the power 3 is 343. So we multiply 343 with 7. So um, so we find that 7 to the power 3 is 343. Then we multiply it with 7, and then we return the value of 7 to the power 4, which is 2401 into 7, and then we return this value to 7 to the power 5. So finally we get 7 to the power 5. So we took 5 steps to go there, and if we want to calculate 7 to the power 11, so we need almost 11 to 12 steps to calculate this. But if we want to try another alternative approach, which is um, this this approach, then notice that what we do is, if we want to calculate a to the power n, we just calculate the power of a to the power half n, and that actually accelerates our calculation. So we want to calculate 2 to the power 12. So if we calculate 2 to the power 12 using this approach, this old approach, we need 2 to the power 12 into 2. Then for 2 to the power 12 we needed 2 to the power 10 into 2, and to calculate 2 to the power 10 we need 2 to the power 9 into 2. So all the way down to 2 to the power 0 into 2. So 0, 1, 2, 3, then 9, 10, 11. So we need 12 steps, but we want to create a shortcut. If we knew 2 to the power 6, if we just knew 2 to the power 6, we could just square it, right? And if we knew 2 to the power 3, we could just square it and then get 2 to the power 6. So now we need to know 2 to the power 3. So if we knew 2 to the power 1, we could square it, then just multiply 2. Then if we somehow, now we don't know 2 to the power 1, but if we somehow need 2 to the power 0, we could just square it and then multiply 2. So how many steps do we need here? So we need 1, 2, 3, 4. So we're going to need 4 steps here. But previously you have seen that this linear approach takes sort of 12 steps, but this is much this just takes 4 steps. So this is much more convenient and more faster in terms of computational complexity. So what we did here is just, if n is an even number, we just since 12 is an even number, so we just need half of its power. So 2 to the power 6, if we just knew 2 to the power 6, we could just square it. But if this was not a if this is not an even number, then what do? We just since this is not an even number, we can write it like this: 2 to the power 12 into 2. But this now is an even number, right? So for that even number, we can do 2 to the power 6 square, then 2. So we use this recursion to get 2 to the power 13. We call this the recursion of 2 to the power 6, 2 to the power 6, and then we square it, and then we multiply 2 to get 2 to the power 13. And for even numbers, to calculate the value of 2 to the power 12, we call the recursion of 2 to the power 6 and then square it, then we get the value for 2 to the power 12. So now let's see how these codes look like. So this is actually the code for the linear approach. We are trying to calculate at the power n, and we're using a to the power n minus 1, then just multiplying 8. And so to calculate to the power 7, look at the number of steps we need here. So we actually needed 1, 2, 3, 4, 5, 6, 7. So to calculate to the power 7, we needed 7 recursive calls. So the linear approach takes a linear time. We want to calculate at the power n, and to calculate that we need n steps. But if we use this approach to calculate at the power n, we just need at the power half n. Then if the number is even, then we square it. Otherwise, we square it, then multiply additional a. So calculate to the power 7, we need just 4 steps. So finally we get 1 to 8.